so many microphones. So these are some surveys. Can you fill them out before, like right at the end? I'd appreciate it. I don't think there's enough, but okay. This is a survey. If you can fill it out at the end. What?
So just give them to people that you think would give you a nice review, right?
They
Started the stream. I'm gonna go
Is there any
run
way to
down.
get more of these? This is like not even enough for like 2 rows.
I'm gonna go get that too.
Okay, thank you. So is it good to start?
Yeah, you can
Well, on
start
time?
whenever you want.
Okay. Okay, thank you.
Is this supposed to be anonymous? It says UCFID.
No.
Okay.
If you don't want to put it, just don't put
Well,
it.
I doubt she's just going to look for it and be like, oh, that's Josh.
Like it doesn't even
so
have the
many bad
letter. It doesn't even have the letter, so I can't even look and be like, oh Jay, that's. Here's a survey. Could you guys fill it out by the end? And there's an extra one, and that's not even up for 2 rows. So they're gonna go get more. They're gonna get more of everything. Another microphone, more tables, chairs.
Thank you so much for doing that. I know it's your job, but like thank
Yeah.
you so much for doing
Yeah,
that.
no problem.
I bought you M&Ms and forgot to bring them. So where can I find you to give you said M&Ms?
I
Find
mean,
her on Facebook.
I don't have Facebook.
Well, she doesn't have it. MySpace,
oh my God, I don't. It's been so many years.
AOL,
I don't even have AOL.
message in a bottle.
Hey, that could work. If I go by the ocean anytime.
Do you have an office so where I can give you your M&Ms? Because I really appreciate the help you've given us this semester.
If you go to the SARC lab,
And leave them there for you.
yeah, so I'll be there tomorrow morning. Like super early.
Because I just want to say thank you because like I probably would not be passing this class if it wasn't for you.
Really?
So,
Oh, I'm
yeah.
glad. Thank you.
All your reviews and stuff, they've been the best. So.
Oh, really? I'm glad. Because like the first 2 reviews, I don't have to do those, but I like to do them. This one I have to do, but I love doing it.
The ones you did for, thank you so much. I didn't even know that was a required of your job. Thank you so much. They saved my ass.
I'm glad. All right. All right, can everybody hear me? It's like super quick. Can everyone hear me now? No? Okay. This is for the recording, and this is for this room. I don't know how to turn it up, and the guy is going to get more surveys, more tables, more chairs.
He worked in IT department.
I never worked with microphones.
He was a level 2 ambassador.
I'm not an ambassador.
No, administrator.
All right, can everybody stop talking really quickly? All right, can everybody hear me now? Yes, okay, so this doesn't really do anything, so. What? I'm sorry. I'll have him fix it when he gets back. If he ever comes back. All right.
Talk it softly.
Talk softly so nobody can.
It's softly.
All right, so before we get started, does anyone have any questions for me? How am I? I'm good. How are you?
I'm fine. How are you?
No questions? Okay, cool. So is everybody able to find this online? So, okay, so this is posted there. I will be posting my solutions after the review. The link to the recording for this is also there. So everything that you should need, you should be set. So my WordPress site. So if you just go to Google and type in UCFSI, click on the WordPress site, click the CECS tab, and then Statics with Tiffany, and it'll be right there. Cool. All right. All right. Oh, and go ahead, if you have your calculators, go ahead and pull them out, just because I want to make sure you guys can calculate them here. So if you're not used to using a particular type of calculator, make sure you can get the right answer here, so that way you'll be fine on the exam. So if you have your calculators, please pull them out now. Do you know how to turn this volume up? I'm so needy, I'm sorry. Thank you. Oh, sorry. Okay, I'm gonna go. All right, here's some surveys. If you fill them out at the end, I appreciate it. Here's some surveys. Could you fill them out at the end? Thank you. Here's some surveys. Here's some surveys. Thank you. Here's some surveys. You get a survey. Everyone gets a survey. Okay. Thank you.
Oh, that's a moment right there. Okay.
right, so the microphone volume is going to be fixed soon, hopefully. So if you guys could just keep it quiet for right now so everybody can hear me, that'd be great. All right, so first of all, what type of problem is this? Shear and moment diagram. So what method do you guys prefer for shear and moment? So I hear areas and integrals. So I did it doing integrals. So we're going to do it doing integrals. If I can try to do it like areas afterwards. Like I know your exam is tomorrow, right? Or some of you is on Tuesday. So I'll see if I can get it done before then, but let's do integrals for this one because I feel like that is the more straightforward one. All right, so what's the first step for the integral method?
Support reaction.
So support reaction. So what type of supports do we have? Pin and a roller. So how many support reactions does a pin have? 2. All right, and then what about a roller? 1. In which direction does it act? So perpendicular to the surface. So get into the habit of saying perpendicular instead of just like up or to the right or something. Okay, by. All right, now what do we do? So we need to solve for these reactions. So which ones do we need, by the way? So we don't need AX, but what is AX? 0. So that's just 0. But what if it wasn't 0? Would it matter at all for this problem? No. So shear diagram, so like shear forces are what direction? So straight up and down. So that one's horizontal, so we don't need it. And it goes through every single point that we could possibly take the moment about. So either way, it'd be 0, wouldn't be included in our equation, so we don't even need to worry about it. So which support reaction do you want to solve for first? By? All right, so how do we solve for by? So take the summation of moments about A. All right, and what do you want our positive orientation to be? Counterclockwise positive. All right, so what should be in our equation? So by, positive or negative? Positive. So we have positive by. What's its perpendicular distance away from A?
8 meters.
So 8 meters. I'm sorry for you guys this way. All right, so by times 8 meters. What else do we have? So you're saying minus this 20. And then what is its perpendicular distance away? So 11 meters. What else?
Applied moment at the end.
So the applied moment at the end, so the concentrated moment. So which direction is that acting? Clockwise, so it's opposite of our assumption, so it will be negative, so minus 150 kilonewton meters. Do we need to include anything else?
Distributed load.
So the distributed load. So what do we call this force right here? Is it a concentrated force?
Negative.
No, so it's not a concentrated force, but it's an equivalent force. So get into the habit of saying equivalent, because whether it's a concentrated force or not, you'll need to know for your shear diagram. So that won't be like a jump up or down. So just keep that in mind. So what will the equivalent force be?
40
So,
times it.
so 320 kilonewtons. All right, so is that going to be positive or negative? So we have minus 320 kilonewtons times what's its perpendicular distance?
4.
So times 4 meters. Do you have anything else to include in our equation?
0.
Nope, so we set it equal to 0. So then what do we get for by? So if you have your calculators out, go ahead and calculate it. Just make sure you get the right answer.
206.25.
So 206.25. So is that positive or negative? Positive. So what does that tell us about our assumption? It was correct. So we assumed it was going up. We get a positive answer. Matches our assumption, so it is going up. All right. So what do we do now? So summation of forces in the y direction equals 0. So what are we going to have in this equation? So AY. What else? So minus 320. Anything else?
Plus B1.
So plus by, which is 206.25. Anything else? Minus 20. Set that equal to 0. What do we get for AY? So 133.75. So again, so that's positive, so it matches our assumption. More tables and chairs are on their way, don't worry. Okay. So now we have our support reactions, the only ones that we care about, and there is sound, yay. All right, so what do we do next? So discontinuities, so draw the lines, right? So just start drawing the lines. So where do we draw the lines on our diagram? So anywhere there's a discontinuity, concentrated force, basically you're looking for points of interest. So what are some points of interest? So where it starts,
Applied moments.
where it ends. So applied moment, so there's only one applied moment at the end, and we already have a line there, so you don't need to worry about that. Where else do we need to include the line?
Distribute load begins and ends.
So beginning and end of a distributed load. So we have one at the beginning, so we need one at the end. Anywhere else? So if there's a concentrated force, so there's a concentrated force right here, but we already have a line. Concentrated force, already line, so we don't need to worry about any others. So then draw the lines for the shear. So this is V of x, and then this would be M of x for a moment. Okay, what do we do next?
Start sweeping from left to right.
So I'm gonna go ahead and write integral method. Okay, so what's the basic setup for the integral method? Where do we start? So point and then what? So point span until we get to the very end. So I'm gonna draw a little line. So we can do shear first. All right, so what's the first point that we look at? So we're gonna look at point A. All right, so point A. So what do we need to ask ourselves at a point? So is there a concentrated force? So is there a concentrated force at A? Yes, so there is a concentrated force. So what's gonna happen on our diagram? So it's gonna be a jump, so up or down? So why is it up? Because it's positive, so it's going up, so we're going to jump up. How much is it gonna jump up? So the value of the shear force at A, and AY is 133, so it's going to jump up 133.75 kilonewtons. So where do we start? Where do we always start on our diagrams? 0. So we're going to start here and go up, and we're going to label that 133.75. All right. So are we done with point A? Yes. So where do we go next? What? Yeah, so it's AY, so we're going to look at this one. Okay, so we did our point. Where do we go next? So span AB. All right, so what do we do for span when we're using integral method? So it's called the integral method. So what do we need to use? An integral, right? Okay, so what's the general equation for integral? Or for the, so V exact. So the integral of omega x dx, anything else? Plus C. All right, what does that C represent?
The value of the force at the beginning of spin.
So the value of the shear force at the left side of whatever span you're looking at. So in this case, this span, what would C be? So 133.75. Now what is omega x?
It's the load.
What is it also called? So distributed load. What else?
It's also called?
Yeah. What do we have to use to find it? Does the equation of a line sound familiar?
Oh.
So we need the slope, or so the equation of a line. So omega x is equal to y, which is equal to mx plus b. All right, so what is the slope?
40.
So think slope is rise over run. So how much does it rise? 0.
Not 0, but it's
So it's not rising at all, it's constant. So since there's no rise, m is 0. But what does b represent? So the y-intercept, so we're looking at the left-hand side. So what is the y-intercept? So 40. So that would just equal 40. So we bring this equation back down. So you have the integral of 40 dx, and then c was 133.75. Now, do we need to include anything else in our equation? A negative sign. Where do we include that negative sign?
only on the integral.
So right here in front of the integral. So be careful, don't distribute that negative to this and the constant, it's just to the integral. Now why do we have a negative sign there? Yeah, so the distributed load is pointing down, so it's a negative shear, so you have to include that negative sign. Now, if the slope is ever like negative, you would include the negative sign in the integral, but then if it's going down, you'd also need to include the negative on the outside and then distribute accordingly. Does that make sense? Okay, so let's say say we have a distributed load like that, like the triangular one. Now the slope of this is it positive or negative? So it's negative. So your m would be negative. So if you have the integral and you have like a negative mx plus b or whatever, you'd also need to include the negative since it's going down on the outside, and then distribute that negative, yeah. So to the mx and the b, since it's the entire equation of the line that you plug into the integral. Make sense? Okay. So back to this one. All right. So we have our integral. So what do we do with that integral?
Integrate.
Integrate, right? All right. So what would we get?
40x, negative
So-
40x plus whatever.
So minus 40x plus whatever. What's the whatever?
133.75.
Plus 133.75. Thank you, Cole. All right. So that's our shear equation. So what do we do with it?
Use it at the point.
So we need to evaluate it at the start and the end point. So what's our start point? 0. And then what's our end point? 8. So we're going to say at x equals 0, shear is equal to what? 133.75 kilonewtons. And if we look back at our diagram, that checks out with what we have, so that's good. And then at x equals 8 meters, how much is shear equal to? Minus 186.25 kilonewtons. All right, so we have our value at the start and the end, but how do we know what it's going to look like getting there? So it's constant. So can we use that little circle? Why not? So it has increasing or decreasing, but is this increasing or decreasing? Neither. So we can't use that. But if it's a constant, what is like the integral of a constant? So like an x, so a positive. Now how do we know if it's going to be going up or down? Because our value is negative, so that's how we get down. So minus 186.25. All right. What do we do next?
Well, you can use that value.
Do we need any other information here? So we need to find this distance. Why do we need to find that distance?
To figure out where your maximum moment.
So whenever shear is equal to 0, what are we going to have? A max moment. So in order to find the max moment, we need the distance. Thank you. All right, so how do we find that value? So we set v equal to 0. So we say when v equals 0, x is equal to what? So plug in a 0 for v right here, and then solve for x. So it would be this divided by 40, which is what? 3.34 meters. All right. So that is 3.34 meters. What was that? How did we get that? So we know that when shear is equal to 0, we have a max moment. So if we go back to our equation, plug in a 0 for this shear, then we can solve for the x. So move the 40x over, and then divide 133 by 40, and then we find. Yep. All right. Do we need anything else for this span now? No? So where do we go next? Point B. So we go back to point span, point span. So point B. So what do we ask ourselves at a point? So is there a concentrated force at B? Yes, so there is a concentrated force. So what's going to happen at B? So it's going to jump up by how much? So by the value of B, which is 26.25 kilonewtons. All right, so what's that going to give us for a value? Where are we going to end up right here? So we're going to end up at 20. All right, do we need to do anything else for that point? So where do we go next? So span BC. All right, and what do we do for a span, for integral method? Nothing. Why? So there's nothing there. There's no shear whatsoever, so we can say that there is no change. So it's going to be what? constant 20. So a constant of 20. All right, so we go back up here, draw a straight line over, and then where do we go? Point C. All right, so what do we ask ourselves at a point? So is there a concentrated force? Yes. So what's going to happen? So it's going to jump down by how much? 20 kilonewtons. So we go back up here, jump down at 20. Are we done?
No.
No, why not?
You have to say yes.
You have to say yes? Okay. I'm going to say no, just in hopes that Dr. Zorn's watching. All right, so we always need to make sure we end back up at 0. So since we did, that's a good way to kind of check our answer. All right, are we done with shear now? Yes, so where do we go next? Moment. All right, so what do we do for moment?
We use the shear diagram.
So we use the shear diagram. So do we do the same point span, point span? Yes, so we look at point A. Now what do we ask ourselves for moment?
Is there an applied moment?
So is there a concentrated moment at A? No, so there's no concentrated moment. So what's going to happen?
Nothing.
Nothing, so no jump. All right, so we do point. Now what's next? So span AB. All right, so what do we do for span for integral method for moment? So the integral of shear. So mx is equal to the integral of v of x dx. Anything else? Plus c. Now what is the plus c in this case? 0, because the left side of the span we're looking at was 0. All right, so what was our equation for shear for that span? So minus 40x dx and then plus 133. Well, that was for the other ones. We include that. Yeah, so don't be like me. Make sure you include it in the entire thing. And then the plus c was 0, so we just leave it like that. All right, so if we integrate that, what are we going to get? So minus 20x squared plus 133.75x. All right. So that's our m of x. So what do we do with this equation? So plug the endpoints, which is what? So 0 and 8 again. So we can say that x equals 0. Shear is equal to what? Moment is equal to what? 0, which checks out with what we have on our diagram. So that's good. And then at x equals 8 meters, how much is moment equal to? So minus 210 kilonewton meters. All right, so we know we need to get from here to negative 210. So how do we know what that's going to look like? The circle. So now we use the circle. So what's the mnemonic for that? Please don't neglect infants. Neglect dumb people instead. I'll draw that bigger next time. All right, so how do we use this?
Look at your shear diagram.
So we look at our shear diagram. Do we look at the entire thing?
No.
So we're going to look at this section first. So is this section positive or negative?
Positive.
So it's positive. Is it increasing or decreasing?
Decreasing.
Decreasing. So it's going to be positive decreasing, so it's going to line up with that one right there. So we know it's going to be something like that. All right, now we look at this one. Is this one positive or negative? Negative. Increasing or decreasing? So it's increasing. So you're going to look at the absolute value of it. So even though it's getting like a more negative number, so like a smaller number, you look at the absolute value. And if you just draw the arrows left to right and it's getting bigger, then you know it's increasing. So negative increasing will look like that. And then we know we need to end back down to negative 210. All right, do we need anything else for the span?
The max moment.
So the max moment. So how do we find the max moment?
Evaluate it.
So we evaluate that equation at 3.34 because that's when shear was equal to 0. So what do we get? 223.61 kilonewton meters. So this value, so this is like right there, so that point is 223.61. All right, now are we done with this span? Yes. So now where do we go? Point B. So is there a concentrated moment at point B? No. So what's going to happen? So no concentrated moment. So no jump. All right, so then where do we go? Span BC. All right, so what do we do for a span? So we use the integral, which equals the integral of v of x dx plus c. All right, what would our plus c be in this case? So minus 210. Now, over here for BC, for the shear, we didn't have an integral, but what would it be? How would we figure that out? Yeah, so look at our shear diagram. So if you look right here, so this is our shear. So this is like a rectangular distributed load. So if we were to do solve for omega x doing the equation of a line, what would the m be? 0, because there's no rise, that would just be 0. So we just have our plus c, which is 20. Now would that be positive or negative? Positive, since it's above the x-axis, or like where the 0 would be. So we have the integral 20 dx plus or minus in this case, so minus 210. All right, so what's the integral of that? What's the integral of 20 dx? So just 20x minus 210. Now, do we need to include a negative sign outside here? Why not? Yeah, so we included shear in this equation, and we already include the negative sign in the shear, like if there was one. So we don't have to worry about that. All right, so what do we do with this equation? So evaluate it. So at x equals 0, what is shear? So minus 210. So if we look at this point, that matches up with what we have on the diagram, so that checks out. And then at x equals 3 meters, what is m? Minus 20. Look at the moment, not the shear. So minus 150, whatever that is, minus 150 kilonewton meters. All right, so how do we know how to get up to that point? So it's going to be a constant. So if we look at our shear diagram, so this is just a constant. We can't use the circle because it's not increasing or decreasing. And since it's a constant and positive, is it going to go up or down? Up. And plus, if you look at our value, we know that it has to go up anyways. So that would be minus 150. Now what do we do? Are we done? No. So we need to look at point C. All right, so is there a concentrated moment at point C? Yes, so now there finally is. So there is a concentrated moment. So what's it going to do? So it's going to jump up by 150 kilonewton meters. So we go back up here, back at the top. Now what do we do? Yes? No. All right. All right, now since we know we need to end up back at 0, and we got to this point, like let's say we look at the moment and we're like, which way does it jump? In this problem, it's easy to tell because we know we need to get back up to 0, so it's going to be a jump up. But what if it was in the center somewhere, and we couldn't tell if it's going to be a jump up or down? What's the typical orientation? What do you think? So clockwise is a jump up. So I know it's kind of opposite of normal convention. So what I just remember is it's opposite of your typical orientation. So like normally we consider counterclockwise as positive, but in this case counterclockwise is a jump down, and then clockwise is a jump up. So that's how to do that. Yes. So clockwise is always going to be a jump down, and then counterclockwise is a jump up. Now, does it matter when you're doing this type of equation? No. So in this case, you can assume whatever you want. You can assume counterclockwise or clockwise, but for the concentrated moment, you have to use that convention. Okay? Any questions on this problem? Counterclockwise is a jump down. Yes. Okay, any question? Yes. How much work? So if you want to do it like this, just do this. So like if you do the point span, say point A, just say no concentrated force, or like if there is a concentrated force. So if there is, say, concentrated force, jumps up or down by this much, do it on the diagram. And then that's good. Yeah, as long as you write it out. So like, so right here, span BC, when there was no change, just be sure to write like no change constant, so that way he knows that that's what like your thought process was. Yeah, that's good enough. All right, any questions? No? Yes. How to do the area method? So I don't have time right now, but for this one, basically it'd be the same thing. So like if you'd look at like the point, include that on your diagram. So you'd say, okay, A is going to go up to here, and then the area. So like the integral method, the integral is just what?
Area under
So the area under the curve. So that's like our curve. So we just find the area of that, which was 320. So if you take this and subtract 320, you're going to get that. And it's that kind of like process. It's a lot easier to do it if you have a rectangular distributed load. If you have the triangular one, it's pretty easy to do the shear. But once you get to the moment, you have to know how to find the area of like a parabola or something. So that's how you do that. Any other questions? No? Okay, so we're going to move on to the next one. Okay, so what type of problem is this one? So another shear moment diagram. All right, so what's our first step? Yes? Yeah, can you guys quiet down so that way everybody can hear, please? Thank you. All right, so shear moment, so what do we do? Or like what method? Integral, because that's how I did it. All right, so what do we do for the integral method? So the reactions, so what type of supports do we have? So pin and a roller again, so we have 2 for the pin. AX, do you even care about AX? No. I'm still going to draw it though. BY. All right, so what do we do next? So go, whatever I want. So draw the lines. So where do we draw the lines? So the beginning and end. Where else? So at B, YB. So it's the end of the distributed load, and there's also a concentrated force there. All right, anywhere else? Nope, there's no concentrated moments. That's the only concentrated force there, there, and there, so we have all bases covered. So we draw lines for shear. All right, so what do we need to do now? So find the support reaction. So which one do you solve for first? So BY. So we take the moment at A, and we'll just stick with our normal convention. All right, so what are we going to have in this equation? So the equivalent force, so where's that going to be located right here, though?
1/3 from the, or from the right angle.
So 1/3 from the right angle, so 2/3 from this distance, so this is what right here? So that's 4 meters. Now what is this equivalent force going to be?
12 times 6 divided by
36 kilonewtons. All right, so which one do you want to include in our equation first? 36, so is that going to be positive or negative? We have minus 36 kilonewtons. And then what is its perpendicular distance away? So 4 meters, or 2/3 of 6. Okay, what else do we have? So BY, is that going to be positive or negative? So plus BY, what's its perpendicular distance? So 6 meters, anything else? The 6, so that's going to be minus 6 kilonewtons. And then its perpendicular distance? right, do you have anything else in our equation? No, so we set it equal to 0. And then what do we get for By? 33 kilonewtons. So it matches our assumptions and it's positive, so it was going up. All right, and then which one do we need to solve for now? So AY, so we do summation of forces in Y equals 0. So what do we have? So we have AY. What else? Minus 36, minus 6, plus BY, and BY was 33. Anything else? So that equals 0. What do we get for AY? So we get 9 kilonewtons, and again, it's going up. All right, so what do we do now? So start the diagram. So I'm going to write integral method again. Okay, so for shear, so what do we do for shear, for integral method? So point span, point span. So we're going to look at point A. So is there a concentrated force at point A? So there is a concentrated force. So where's it going to jump? And by how much? Jumps up by A, which is 9 kilonewtons. So we start at 0 and then jump up to 9. All right, anything else for this point? Nope, so we go to which span? So span AB. So we need to do our integral equation. All right, what is our plus C in this case? 9, so it's at the left side of the span that we're looking at. All right, and then so how do we find omega x? So omega x, I'll just plug in. So equals the equation of a line, so mx plus b. All right, so what is m? So 2, so how do you get that though? So rise over run, so the rise is what? And then the run is 6, x, and then b was what? So plus 0. So that is our y-intercept, which is 0. And that gives us 2x. All right, so what do we do with that 2x now? So plug it back into our equation. So do we need to include anything outside of this integral? So the negative. So the shear force, or the shear distributed load is going down, so we need to include a negative right there. So we'd have a negative integral of 2x dx plus c, which of c was what? So plus 9. All right, so what does that give us when we integrate it? So minus x squared. Anything else? Plus 9. All right, so that's our shear equation. What do we do with this? So our endpoints are what? So 0. So when x equals 0, shear is equal to what? So 9 kilonewtons. So if we go back up here, that checks out with what we have, so that's good. And then what other value do we plug in? So 6 meters. So x equals 6 meters, shear is equal to what? So minus 27 kilonewtons. So we need to get to here, so minus 27. So how do we know what it's going to look like? So look at our equation. So this is our equation, so it's minus x squared. So if it's x squared, it's going to look like what? So parabola, and that negative sign tells us what? So it's going to be concave down. So let me see if I can draw. Okay, so that's supposed to be a parabola. And then this value was minus 27. All right, are we done with this span? No, why not? We need to find this x value right here. So again, so when shear is equal to 0, x is equal to what? So plug in it 0 right here, solve for x, so x is equal to 3 meters. So that's 3 meters right there. All right, now are we done with the span? Yes, all right, so where do we go next? So point B. All right, so is there a concentrated force at B? Yes, so it's going to jump which direction by how much? So there is a concentrated force. So it's going to jump up by 33 kilonewtons. All right, so what's that going to give us for a value right here? So that's going to give us 6. All right, where do we go next after point B? Span BC. So what's going on with span BC? Absolutely nothing as far as we're concerned. So no change. So it will be constant. All right, now where do we go? Are we back at 0 yet? No, so we need to look at point C. So is there a concentrated force at C? So which direction is it going to jump by how much? So it jumps down 6 kilonewtons. By 6 kilonewtons. And then we end back at 0. Are we done now? Huh? After a yes? Okay. No, I just want Zorn to watch this and see. It's okay, I'll show him, don't worry. All right, are we done with this side, or with the shear? All right, so where do we go next? Moment. So again, we start with point A, so point span, point span. So is there a concentrated moment at A? So no concentrated moment. No jump. So we just stay at 0 for right now. All right, now where do we go? So span AB. All right, so we need our equation. So the integral of v of x dx plus c. What would our c be? 0 again, because the left side is just 0. All right, so what was our shear equation? So we had minus x squared plus 9 dx plus 0. So when we integrate that, what are we going to get? So minus 1/3 x cubed plus what? Plus 9x. So what do we do with that equation? So endpoints, so at x equals 0, what is shear? 0, which checks out with what we have here, so that's good. And then what other value do we plug in? So x equals 6 meters. Moment is equal to what? Is it 0? So minus 18. All right, so how do we know how to get from here down to here? You just don't?
No, please don't.
Okay, that makes sense. So use the circle. So again, so please don't neglect infants, neglect dumb people instead. Okay, so what do we do? Huh? So we look at this side, so is this positive or negative? So this is positive. Is it increasing or decreasing? So it's going to be positive, decreasing. So it's going to look like that. All right, now we look at this section. Is this positive or negative? Increasing or decreasing? So it's negative, increasing, so it looks like that. And we know we need to get down to minus 18. All right, do we need to do anything else for this span? So the max moment, so m, it's supposed to be max, is equal to m at what value? 3 meters, which is what? 18 kilonewton meters. So this right here is 18. All right, are we done with this span now? Yes, where do we go next? So point B. So is there a concentrated moment at B? No, so we say no concentrated moment. So no jump. All right, now where? Span BC. So what do we do for this? So we need our moment equation. Okay, so what goes inside this integral? 6. Positive or negative? So positive since it's above. What is our plus c? So minus 18. So what's that going to give us for our equation? Yes. So 6x minus 18. What do we do with this equation? So plug in our values. So x equals 0. M is equal to what? Minus 18 kilonewton meters. And if you look back up here, that checks out with what we have. So that's a way to confirm. And then at x equals 3 meters, what is the moment? 0. All right, so how do we know how to get from here to here? So it's constant. So if you look at our equation, so it's 6x and it's positive, so it's going to be linear going up with a positive slope. Back to 0. All right, and then what do we do? Okay, I'll write yes this time. Yes.
When he asks for maximum moments, isn't it also the highest and lowest?
It depends on what he asks for, because like back in like whatever math class it is, it depends on like a certain value, but he should specify what it is.
So like the maximum moment in this case would be 18 and
Yeah, it depends on if it's like the magnitude. So if it's the magnitude, then it's technically the same. If not, then yeah. He should specify, yeah. All right, any questions? Yes.
Yeah. With an internal hinge, do you have to draw a discontinuity?
So with an internal hinge, so if there's an internal hinge or an internal pin, those forces or like the reactions are only internal, so there's no external. So you're only going to look at your external concentrated forces. Make sense? Cool. Yes.
How would I determine the
Hey man, shut up.
how would I determine the x and the shear if I used area?
So if you used areas, so again, so you do the same process in a way. So like you look at your point A, so you'd say, okay, this is for the x. That was one of the ones where he drew like the weird parallel lines and then like that height.
Oh, you can just
Huh?
use triangles.
Yeah, like he used those lines to find a triangle and then use that. But for that one, you need like the area of this to find like this value. But when you try to do that, so like this is a parabola. So unless you know the area of a parabola off the top of your head, then this part could be a little difficult. Huh? Okay. Any other questions? Yes. Yep. Any questions? Yes. So with the parabola, like for the area method? Okay, so that one, I haven't really done the areas method too much, but he did like the parallel lines, and so like the similar triangles thing, and so that's how you would find the x value. So you'd say like, okay, so 6 is to whatever as some x value is to whatever value. Huh?
Hey, you could still draw triangles.
Yeah, it'd be easier if it was like linear. I personally don't know how to do it with the parabola method. I've never done the area method for a triangular distributed load, just the rectangular one. So I personally don't know for that part. Okay. Any questions? Any more questions? Yes. Can you guys be quiet really quickly?
Hey, keep it down!
No, there's no moment. There would only be a concentrated moment at A if it was included, or if it was a fixed support, then there would be that concentrated moment. Cool. Any other questions? Yes. Mm-hmm. Yeah, so where you draw the line, so it's always going to be beginning and end of the beam, beginning and end of a distributed load, wherever there's a concentrated force and wherever there's a concentrated moment. Yeah, so like if it's an internal hinge or an internal pin, since it's only internal, you wouldn't have to draw that, because for these, you're only looking for external concentrated forces or concentrated loads. And that's, again, what I was saying. So like this force right here is not a concentrated force. It's just an equivalent force. So if that was a concentrated force, then we would draw a line there, but it's not. So just make sure you can tell those apart.
Did you determine X to be 3 meters?
Yes, 3 meters. Did I write it wrong? Yeah, so 3 meters right here and then right here. Okay. Any other questions? No? Okay, so let's move on to the next one. All right, so what type of problem is this one? Centroid. So what is our general equation for this type of centroid problem? You don't remember off the top of your head? So x bar is equal to what? So x dA. What goes on top of this x? A squiggly. Or tilde, whatever. It doesn't matter. When I took this class, my professor actually used the word squiggly, so it's like permanently embedded into my brain. Okay, and then what goes on the bottom? Integral of dA. And then what about y bar? Same thing, but with a y. Squiggly. All right, so based on our equation, what are we going to need to do? Or like, what do we need? So we need dA, and we need x squiggly, y squiggly. So how do we find those? What do we need to draw? Squares? Is it square? It's a rectangle. So which one do you think would be easier to use? The horizontal or the vertical? So yeah, in this case it would be the vertical one. After you're done with that, if you want me to just show you like the solution for the horizontal one, I will. It's a lot less pretty, but I'll show you the two of them. All right. So what does x squiggly and y squiggly represent? So the location. So the centroid of what? So this represents the centroid location of our differential element. So y squiggly is going to be from the x-axis to right here, and then x squiggly is going to be from the y-axis to right here. All right, so how do we go about labeling this? Like, first of all, what is this value right here? That's dx. Now, how do we know what to label x or y? What's this value right here? So this entire length is y, so what's this distance to right here? So y over 2, which is equal to y squiggly. What's this value right here? So x, which just happens to be what? So x squiggly as well. Now, does anyone confused on how to label them, like what you label as x or what you label as y? Yeah, y over 2. So y squiggly is the distance from the x-axis to the centroid of the element. So if this whole thing is y, then this is half of y. Okay. Is anyone confused on how to label it? Where do you have it? You got it? Okay. So now we need dA. So what does dA stand for? Like, what does it represent? So the area of what? Of the differential element. So the differential element is a rectangle. So the area of a rectangle is just length times width, or base times height. So what would that give us for our dA? So y dx, so the height times the width, so y dx. All right. So let's go to our equation. So x squiggly was just what? So it's just x. And then what was dA? So y dx. Right? And then on the bottom we have dA, so again it's just y dx. All right. Now how do we know what our boundary conditions are going to be? So 0 to b. So how do you know what's with respect to x? Because we have dx. So if you remember back in calculus, like when your professor would read this, it'd be the integral of something with respect to x. So if your differential is with respect to x, your boundary conditions also have to be with respect to x. So it's not because we're solving for x bar, it's just because this is dx. Make sense? Okay, so this would be 0 to b, and then 0 to b again. All right, so what do we do with this equation? Can we integrate it exactly how it is right now? So what do we need to do? So replace y in terms of dx. Since that's our differential, we can't change it unless we use the other element. So do we have an equation of y in terms of x? Yes, so what is it? Actually, I'll go over here. So you have x times, and then what was y? So h over b squared x squared dx. And then this would be 0 to b. And then h again, or h over b squared x squared dx. Okay, can we do anything with this to simplify it a little bit? So pull out the constants, so h over b squared, 0 to b, and what goes in here now? So x cubed dx, and then again we can pull out the constants, so h over b squared, 0 to b, and then what's on the bottom? Or what goes in the integral? So just x squared dx. Now what happens with these constants? They're the same, so they just cancel. So now, so if we integrate this, what's that going to give us on the top? So 1/4 x to the 4th from 0 to b, and then what goes on the bottom? 1/3 x cubed from 0 to b. So that's going to give us, so b to the 4th over 4 over b cubed over 3. So what's that going to simplify to? So 3/4 b, so you can multiply by the reciprocal and then get 3/4 b. Are we done with this one now? Yes. So we can go ahead and put a box around it. Now, even though this one's in terms of like variables or constant, is there a way we can still check our answer to see if it makes sense? Yeah, so just look back up here. So let's check to see if our answer makes sense. Would it make sense for the centroid of this entire shaded area to be somewhere right around here? Yeah, now what if we got 1/4 b? Does that make sense? No, so that's when we can kind of check your answer. So if you get like 1/4 in this tiny little corner, you know that it's wrong, and then you can go back and change that. All right, so let's do y bar. So what was y squiggly? So y over 2. And then dA was y dx. So what's our boundary conditions now? So is it the same? Ooh, is it h? No, so it's 0 to b. So even though we're solving for y bar, our differential is still with respect to x. So since our integral is with respect to x, our boundary conditions also have to be with respect to x. All right, and then so on the bottom is dA, so y dx. And then this is also 0 to b since it's dx. All right, so what do we do from here? Can we pull anything out? Are there any constants we can pull out? So 1/2. So let's go ahead and pull out a 1/2. 0 to b. So then we just have y squared dx over y dx. Now what do we need to do with this? So plug in something for y in terms of x. So we have that equation right there. So let's go ahead and do that. And it's squared, so h over b squared, x squared, and then that entire thing squared, dx over the integral of 0 to b, and then y is h over b squared, x squared, dx. All right. So what would that give us once we square it? So, and let's go ahead and pull out our constants in the process. So we have a 1/2, and then what is h over b squared squared? So h squared over what? So h squared over b to the fourth, the integral of 0 to b, and then what's left in the integral? X to the fourth dx, and then bring out the h over b squared, and then just x squared. All right, so what is the integral of this? So 1/5 x to the fifth from 0 to b over h over b squared. And then what's the integral of this on the bottom? 1/3 x to the third from 0 to b. So plug in our values. So b to the fifth over 5. And then b cubed over 3. Yeah. All right, since we're running out of room, so normally to simplify this a little bit, so what would be on the top? So go ahead and simplify the top first and then the bottom. So what would be on the top? So you're saying bh squared, anything else? So over 10. So 2 times the 5. Right, and then what goes on the bottom? So bh over 3. So multiply by the reciprocal, and that will give us 3/10 h. All right, now can we check our answer again? Yep, so if we go back up here, would it make sense for it to be somewhere right around here? Yeah, now what if we got like 9/10 h? 3/10 h. Yeah, you should be concerned if you get 9/10 h. All right, does anyone have any questions on this problem? Yep. So can we do this problem another method? Yes. Double integral, so that's one way. Is there another way? So we use the vertical differential element. Can we do the horizontal one as well?
Yeah.
Do you want to see it?
Oh, it's horrible.
It's horrible, you just did it?
Yeah.
Yeah, it's not pretty. So if you look at this problem, like the integrals, they don't look too bad, right? But then if you do it the other way, they're much longer and less nice looking. So how do you tell which one's going to be the easier method? You start doing it. So basically the easiest way to do it, so if you look at your equation, you're going to need x squiggly, y squiggly, and dA. So draw the element, solve for x squiggly, y squiggly, and then your dA, and that's going to tell you how it's going to look. So if you look at dA, it's y dx. That's as good as it's going to get. So that's as nice as it could possibly be. And that's just x, and that's y over 2. It's not bad at all. But if you look at this one, x squiggly is x plus b over 2, and then y squiggly was just y. But then dA, where's dA? So dA is b minus x times dy. So if you plug that into this equation, you have this times that, and you have to distribute, and it's really easy to mess up. So just solve for your x squiggly, y squiggly, dA, and that's going to tell you which one's going to be easier looking. So solve for the x squiggly, y squiggly, dA, and then that'll tell you how it's going to be. So like for this one, they were really simple. For this one, it's like something in parentheses times something in parentheses, and it just kind of ugly. All right, any questions? Yes. 3/10 h. Yeah, so if you do it this way, you still get the same answer, but it just takes longer. But I will upload this solution as well to my WordPress site, so if you want to see it that way, go for it. All right, any questions? No? Okay. All right, so what type of problem is this one? So another centroid, but what type of centroid is this one? So composite. So what's our formula for that one? So this one we only need y bar. So what's the equation for y bar for a composite shape? So summation of AI times what? Yi over the summation of AI. All right, so what do we have to do for these type of figures? So make a chart, and separate them into what? So composite figures. So what are we going to need to calculate for these? The area. So you need to find shapes that you know the area of off the top of your head. So what are some shapes that you see? 2 circles and a rectangle. Now if we make that like a circle, what's going to happen right there? Is it going to be a perfect rectangle and a perfect circle? No, but what does it tell you in the problem? So neglect those little corners so you don't have to worry about them. So let's call this figure 1, and this one's 2, and then let's call this one 3. All right, so now that we have them labeled, what do we need to make? A table. So what do we need to include in the table? So the figure. What else? Area. And then what units is the area going to be in? Millimeters squared. All right, anything else? Or what else are we going to need to include? This is 110.
So for y, you're going to need the y distance.
All right, so then we're going to need yi. And then what units is that going to be in? So that's millimeters. Do we need anything else? So we need AI times yi. And then what units is that going to be in? So is it squared? It's cubed. So it's squared times 1. All right. So let's start with figure 1. So what is the area of a circle? So pi r squared. What's r? So it's half of 35, which is what? I'll just put 35 divided by 2. Yeah, so be careful with this one. So that's actually the diameter given, so don't look at it and immediately think it's the radius. So pi r squared. And what value will that give us? So 962.11. All right. Now what's yi? Or like what does yi represent? So the distance from the centroid of that shape to what? The x-axis. Now does it give us the x-axis in this case? No. So if it doesn't give it to us, can we draw it wherever we want? But can we draw it wherever we want in this problem? Why not? So it tells us where it should be. So like what does y bar represent? So the distance from the centroid of the entire figure to the x-axis. So if that's the centroid, it's telling you that the x-axis has to be right here. So if it didn't give you that and it didn't give you the axes, then you can put them wherever you want, but because it shows that, that's where you have to put it. So always look for that just in case. All right, so the distance from the x-axis to the centroid of the circle is how much? So 177.5, so you need to go up 50, up 110, and then up 17.5. All right. And then what is AI times yi? So 170,774.525. All right. Let's move on to figure 2. So what type of shape is figure 2? So it's a rectangle, so it's going to be length times width, so 110 times 15, which gives us what? So 1650. What's yi? So 105. So it'd be up 50 plus half of the 110, and then what's AI times yi? So 173250. Okay, and let's move on to figure 3. So again, pi r squared. So pi, what's the radius in this case? 25 squared, which gives us what? So it should give us 1963.495. And then what's yi? 25, and then ai times yi. So 49087.375. All right, so what do we do with this chart? So which ones do we need to find the sum of? So area, and then ai times yi. All right, so the sum of ai is what? So 4575.605 millimeters squared, and then sum of ai yi is equal to what? Anybody get it? Yep, so 393,111.9 millimeters cubed. All right, so now that we have these values, what do we do with them? So go back up to our equation. So I'll write it out again. So sum of ai yi over ai. All right, so which value goes on top? So ai yi, which was 393,111.9 millimeters cubed over 4575.605 millimeters squared. So what is that going to give us for our y bar? So 85.91 millimeters. All right, is that our final answer? Yes, so let's go ahead and put a box around it. All right, now can we check this answer for the composites as well? So kind of, so what's exactly halfway for here, for this entire distance? So like the 50 plus 110 plus 35. Yeah, divided by 2. How much was it? So 97.5, so that's halfway. So this is below that, so would it make sense for it to be slightly below halfway? Yes, because the bigger circle is on the bottom. Now if it was above halfway based on the axis, then you know that it's wrong. Make sense? All right, does anyone have any questions on this problem? Yes? The third one? This column? This yi? Okay, so this yi, so y bar is the distance from the x-axis to the centroid of the entire shape, and then yi is the distance from the x-axis to the centroid of that figure. So since this one is the circle, so the centroid's right in the middle, so to get this value, we have to go up 50 plus 110 plus half of 35, and that'll give us that. And then this one's half of that, so 25, and then 50 plus 110 divided by 2. Cool. Yes? You mean start like 1, 2, 3? Yeah, you can do it in whatever. Yeah, you can start whichever. Or you mean like where you put the x-axis? The x-axis, so in this problem, it wasn't given to us, but it did tell us where y bar was. And so y bar represents the distance from the centroid of the entire figure to the x-axis. So since it's saying from here to here, that's y bar. If this is the centroid, this has to be our x-axis. If it didn't give us y bar telling us right there, if it didn't give us the x-axis, then you could put it wherever you want. So then you could put your x-axis right here. Make sense? Okay, cool. Any other questions? No? Okay. All right, so what type of problem is this one? So moment of inertia. So what's the general formula that we use for this type of moment of inertia problem? So let's start with Ix. So what's the equation for Ix? So the integral of y squared dA, and then Iy is what? Integral of x squared dA. All right, so what do we do next? So draw your differential element. Now, can we use the same one for either of these equations, or either value? Technically, yes, but if we want to use just this equation, which element do we have to use for x? So y over 2. So are we going to use, so for Ix, to use just this equation, are we going to use the axis that, or the element that's parallel to x, or parallel to y? So parallel to x. So for this one, I'm just going to draw like the two separate figures over here, so it's easier to see. All right, so for this one, let's use that. What's this value right here? So that's dy. All right, and then so that's y, x. All right, so what do we need based on our equation? So this y, is it just a y or is it y squiggly? So this one's just a y. So there's no tilde on this particular one. I'm sorry, Jay. Sorry. All right, so what is this value right here? What's that distance? Or what do we label it as? Or actually, do we need that distance at all? No, so why not? Yeah, we don't care. So the equation was just y, or just y, so we don't need to worry about the y squiggly at all. All right, but what do we need? So we have dy right here, so we need dA, we see in our equation. So we have the height. What's this length right here? Or first of all, what do we label this? So that's x. So this distance, so if this is b and this is x, what's this distance? So b minus x. So what is our dA for this case? So the area of the differential element, so length times width, so b minus x dy. All right, so we plug in, so y squared, and then dA, b minus x dy. Now, what are our boundary conditions? So 0 to b or 0 to h? So it's 0 to h. So even though we're calculating the moment inertia about x, our differential element is with respect to y, so our boundary conditions also need to be with respect to y. All right, now can we integrate it just how it is right now? Yes, thank you. So can we integrate it just how it is right now? No. So what do we have to do? So get x in terms of y, so how do we do that? So we have y in terms of x cubed. So we just solve for x in terms of y. So that'll give us b over h to the 1/3, y to the 1/3. So just multiply y by b cubed over h, and then take the cubed root of that. All right, so we have 0 to h of y squared times b minus b over h to the 1/3, y to the 1/3 dy. All right, so what do we do with it now? So can we integrate it just how it is right now? No, so we need to distribute that y squared. So what do we get for our first term? by squared minus, what's that going to give us? So let's keep our constant. And then what would y squared times y to the 1/3 be? So it'd be 7/3. Yes. Does anyone not understand that? Yeah, okay. So y to the 7/3. So you think about if you're multiplying two exponents, you add them. So you have to get common denominator and then add them. So you'd make that a common denominator of 3, and then, so it would be 6/3 plus 1/3, which is 7/3. Make sense? Okay. Okay, so how, like, what do we get when we integrate this term? by cubed over 3 minus, what's this one? So minus 3/10 b over h to the 1/3, and then what would y be? So 10/3. So again, so you're adding a value of 1 to it, so then you do 7/3 plus 3/3, which gives you 10/3. 0 to h. I'm not sure what happened to the microphone, but hopefully you can hear me. All right. So now we just plug in h wherever y is, so we get b h cubed over 3 minus 3/10 b over h to the 1/3 h to the 10/3. All right, so can we simplify this term at all? No. So just leave it as bh cubed over 3, and then what will this term simplify to? So we have 3/10, and then we have b, but what does this h simplify to? H to the 3rd. So since you're dividing, you'd subtract your exponent, so 10/3 minus 1/3 is 9/3, which is 3. So then we would just have b h cubed. All right, so now we have bh cubed over here and bh cubed, so can we simplify that a little bit more? So what would that be? Or what would we have to do to get that? So common denominator. So what's a common denominator? 30, so what would go on top right here? 10 bh cubed minus, so then times 3, so 9 bh cubed. So what will that simplify down to? So 1 over 30 bh cubed. Now, can we check our answer with this type of problem? No, because what units would it be in? Like, let's say we had units of distance were meters. What units would this be in? So meters to the 4th. So a value, or like a unit of distance to the power of 4. Can't really check for that, unfortunately. But what should this answer always be? It's going to be positive or negative? So it's always going to be positive for this case. So if you get a negative answer, like if you got like 9 over 30 minus 10 and you got a negative sign, that should tell you that it's wrong. All right, so let's move on to IY. So if we drew the element that was parallel to x for IX, which one are we going to draw for IY? So parallel to y. All right, so what's this going to be? The dx or dy? So it's dx. What is this height? So just y. All right, so what is our dA going to be for this one? Y dx, that's as good as it's going to get. All right. So we integrate, so keep the x squared. dA was y dx. Now what are our boundary conditions going to be? Is it 0 to h or 0 to b? So 0 to b, so again, look at the differential. So since it's with respect to x, our boundary conditions also have to be with respect to x. All right, can we integrate it how it is right now? No, so we need to get y in terms of x. Do we have an equation for that? Yes. So 0 to b, so we have x squared, and then y is h over b cubed, x cubed, and then dx. All right, so can we bring anything out of this equation? So we can bring out h over b cubed, and then what's left on the inside of the integral? So x to the 5th dx. All right, so we bring down the constants. What's the integral of x to the 5th? So x to the 6th over 6 from 0 to b. So bring your constants down again. And then we have b to the 6th over 6. So what's that going to give us for IY? So 1/6 hb cubed. All right, can we check this answer? No, because it's going to be in units of distance to the power of 4. There's not much we can do with that. All right, does anyone have any questions on this problem? Yes. For IX was 1/30 bh cubed. All right, any other questions? Yes. So can you solve it with the other differential element? Yes. So you can do it, but you'd have to use parallel axis theorem. And it's a lot less pretty for the integral method, like when you're doing it about areas. But you guys want to see it? No? Some people are shaking their head like no. Okay. I'm going to show it anyways, just so you can be thankful. Like if you think this is bad, just hang on. Just 1 second. Okay. Yeah, basically. Like I did this for fun. Not really, but. Huh? I do this because I care. I want you guys to learn. So if you do attempt to do it the other way, this way you can check your work. Okay, so this doesn't look so bad, right? So IX was pretty straightforward, wasn't so bad. This was awful. The first time I ever did this, I wasn't getting the right answer and I couldn't figure it out, but I just multiplied, like, I distributed something wrong. But yeah, that's what you would have to do. But you still get the same answers. Yeah, so basically like the parallel axis theorem. So technically whenever you're doing moment of inertia, you always do include it, but sometimes depending on what you use, your little like y squiggly or x squiggly is just 0, so it cancels out. And that happens if you do use the element, that's the wrong one, the element that's parallel to that. So if you see for this one, for IX, you have a y squiggly right here. So that's the distance. But if you look right here, at every point from the x to here, that y value is the same, which is why you don't have to worry about it. But for here, every point along the element, y is changing, which is why you have to include it. Okay? But yeah, that's how to do that. All right, does anyone have any questions on either method? Besides why? No? Okay. All right, last problem. We're almost done. Yay. All right, so what type of problem is this one? Composite. So composite what? So a composite moment of inertia. So we're trying to find which one? IX or IY?
We know our IX is.
So IX. So what's our general equation for IX for composite bodies? So summation I naught x ADY squared. So what's this part called? Parallel axis theorem. So again, for this case, you technically always have to use it, but in some cases it's 0, so you don't even worry about that. But we'll show that in just a little bit. All right, what type of shape is this? A composite shape. Do you have any word to describe this though? A rectangle? Some spheres missing? Okay, so if we had like a rectangle with a little circle in it with like a hole through the figure, how would we find that? So you take the rectangle, moment of inertia, minus the circle. So in this, what shape should we start with? So let's start with like, I can't draw, so bear with me. So you want to start with that shape. So we start with a rectangle. And what do we do to that rectangle? So subtract like these little things. But do we know the moment of inertia for just those little shapes? No? Or yes? Let's see.
Yes.
So if you open your book for the first time this semester, you will see, so we have triangles, rectangles, circle, semicircle, quarter circle, circular. So lots of circles, basically. But do you see one that's like that little sliver? No. What? Where?
Yes.
They add up to be. All right, so based on like the information that's given though, so we have a rectangle. What other shape do you see? So you see this shape, right? Do you see that shape in the book? What's it called? So is it the quarter circle? It's the circular sector area. Huh? So there's two of them. So in this case, yeah, so it's 45 and 45, so 90. But if you look at how it's given, the one that we have is like rotated, so it's symmetrical, but this one's not. Make sense? Yeah, so that would just be a lot more work for yourself.
Circular area either.
Semicircular? No, based on, yeah, so the angles that are given. All right, so we have that circular sector area. So what would we need to do with those two shapes? Would we add them? So we would subtract 2. Hang on. So minus 2 of those. Are we done now? No. What do we have to do to it now? Do we add or subtract triangles? So we need to add how many? 2? 4. Is it 2 or 4? 4. Yeah, that's why I did it. That's why I did it.
Who made that?
I don't know, but they must hate people. Is anyone confused on this? Everyone. Okay. Hang on. Give me a second. What? True. Yeah. You could do it that way and then just subtract the triangles. There's like multiple ways to do it. Okay. Hang on. I was prepared for this.
You are so smart.
Okay. Yes, I came prepared. All right, so let's say we're starting with a rectangle, right? Yes, I did cut it. That was the hardest part of this review, trying to cut these perfectly. But anyways, all right. So if we took the rectangle and we had subtracted 2 of these little blue areas, we'd be done, right? But do we know the moment of inertia off the top of our head for that? No, but we are given information for these sector areas. So we subtract 2, but you can't subtract this space from nothing, so you have to add back. Give me 1 second. Oh my God. 1 second.
I'm so impressed.
There's a question on the survey that's like, oh, were they prepared? Check. Oh my God. All right, hang on, let me try to do this. Okay. So add 1, 2, 3, 4. Okay. So we have to add 4 back. Does that make sense? Is it easier to visualize now? Okay, cool. All right, so let's get this out of here. All right, so back to this. All right, so minus 2 sectors plus 4 triangles. So let's start with the rectangle first. All right, so what is the moment of inertia for a rectangle about the x-axis? So if you're not sure, Ix is 1/12 BH cubed. So what's the base in this case?
Whatever you want it to be.
Whatever you want it to. So this is A and this is A, so what's this entire length?
Oh,
So
the base
2A,
is
so,
the reference.
hmm?
The base is the reference.
Yeah, so like the base of the triangle, yes.
These equations, are they being provided or we have to know them?
I believe he said he was going to give you
That exact.
this chart, but he's not going to tell you how to use it. So if you see like some of these, the axes are going directly through the centroid and sometimes they're not. What would, like, how do you know how to use that? Like, what would you do? Like, how would it be different?
If what?
Like to solve for like the IX.
If
All right.
reference wasn't there?
So think back to like our general equation, which was I naught x plus 80y squared. So this part is the parallel axis theorem. So what does dy represent?
Distance and y from the centroid.
So the distance from the x-axis to the centroid of that particular figure. So if you look right here, for the circle, what's the distance from the x-axis to that centroid? 0. So for this particular shape, if it was going directly through there, you wouldn't have to use parallel axis theorem. For this one, you would, since your dy is going to be whatever distance that is, and that tells you. So that's the only difference. You just have to know if you're going to use parallel axis theorem or not. So if you're ever not sure when to use it, just use it every single time, and you'll see when dy is 0 and then when it's not. Okay, so what was our base? Yes. The figure on the book?
Now let's say where there's rectangle, how from the x-axis to the centroid, what axis is
The circle or the semicircle? Semicircle? Yes. Yeah, so if you were calculating IY, then it would be dx, and then that value is 0. Yeah, good question. All right, so what's our base? So 2a, so 200. And then what's our height? 25. So we need this entire length. So we have b plus b. How do we find this distance right here? So r is 200, so what would this value be? So then that would be 200 sine of 45. And then we have 2 of those plus 2b, which gives us what?
2 times that.
2 times a
2 times whatever, 200 sine of 45
plus 2b.
plus 2.
Yeah. So it should be this value, so 332.427, what? 340? For what? So it should be 200 sine of 45 times 2 plus 25 plus 25. And that should give you 332. All right. So then that value, I'm just going to go ahead and give it to you now. So 614, 5, 6, 2, 2, 8, 9. These ones get really long. But what units is this going to be in? So millimeters to the 4th. All right, are we done with the rectangle? No, why not? So the parallel axis theorem, which includes, no, we can. I'll show you how to like set it up at the end. So plus a, so what's the area of a rectangle? Actually, doesn't matter. So a dy squared. So what's dy for the rectangle? 0. So it's the distance from the axis you're taking the moment of inertia about to the centroid of that shape. This centroid also happens to be the centroid of the rectangle. So that dy is 0. So you don't have to use parallel axis theorem. But if you're not sure when to use it, just always include it, and you'll see when it's 0. All right, so let's go to the sector area. So what is the moment of inertia for the sector about the x-axis? Don't hold back. Tell me how you really feel. So, explain dy. So dy represents the distance from the axis you're taking the moment of inertia about to the centroid of that particular figure. Yeah, you have a question? Another one? No? Okay. Okay, so it's 1/4 r to the 4th times theta minus 1/2 sine 2 theta. Hang on, I'll answer that in a second. All right, now, this theta, does it matter if we keep it in degrees or whatever? Or can we keep it in degrees? Yeah, as long as your calculator is in degrees, you can leave that in degrees. What about this one? Can we leave this theta in degrees? No. You have to convert it to radians. I'm pretty sure it's because, like, if you put it in your calculator, so if you include 2 theta and your calculator is in degrees, if it's in the sine function, it recognizes that it's degrees. But if it's just out here, it won't recognize it, so you just have to convert it to radians. So r is 200 to the 4th. So what's our theta? Is it the 90 degrees or the 40 degrees? Or 45? So theta is just this little one, so 45 degrees. So what is 45 degrees in radians?
Pi over 4.
Pi over 4 minus 1/2 sine. Can we convert this to radians if we want? Yeah, but then your calculator would also have to be in radians, and then if you go solve another problem and it's in radians, then everything would be wrong. So I recommend just leaving this in degrees so that way you never have to worry about your calculator. Yes? So you need radians, probably. Yeah. So sine of 2 theta, so what's 2 theta? 90 degrees. All right. Now let's say plus a dy squared. What's dy? So if you're not sure, let's look back at this. So this tells us where the centroid lies. So if the centroid lies on the axis, what's our dy? So our centroid would be somewhere right around here. So since there's no distance away, this is 0, so you don't have to worry about that for this shape either. All right, so this is going to be 114, 159, 265.4.
So you're adding in the complete center and just subtracting out the
What?
triangles.
No, we're adding the triangles. So basically, I'm just finding the Ix for each individual one, and then I'll go back and plug it into like that general equation. It's like I'll take the.
Ix for this sector.
Huh?
That was Ix for the sector, right?
Yes, this is Ix for the sector.
So that's the whole sector.
Yeah, so this is just for the one sector.
So then it's overlapping the rectangle you just found, so you're subtracting it out. Okay.
Yep, but you can't subtract these areas from nothing, so then you have to add the 4 back.
So then you have to add it. Okay.
Yes, okay. And then we have the triangle. So Ix for
1 over 36.
triangle, so 1 over 36 BH cubed. So how do we find the base of that triangle? So that would be 200 cosine 45. And what is that value? Did anyone get like 147 or 141? For 200 cosine 45? Yeah, okay, so this should be 141.42. All right, and now how do we find the height of the triangle? So then 200 sine of 45, which is the same thing because sine of 45 and cosine of 45 is the exact same thing. So I'll type in or write 141.42 cubed. All right, do we need to use parallel axis theorem for this one? Why or why not?
Because of the distance from the centroid to.
So there is a distance. So dy is not 0 this case, right? All right, so dy represents the distance from the x-axis to the centroid. So what's the distance from, or where is the centroid of a triangle located in terms of like the y distance? So 1/3 from the right angle, so this will be 1/3 of the height. The height is r sine of 45, so 200 sine of 45. And what will that give you? So we'll do the area, so 1/2 base, so 200, so that's 141.42 times 141.42 times dy, so that's going to be right here. So what's our dy? So approximately 47, and that is squared. So if we simplify this a little bit, 3333.2054.68. These are really ugly. Okay, so now we have the basic ones for each individual shape. So what do we do from here? So a little zoom in? Okay.
Positive, whatever the rectangle is.
Yes, no problem. Yes, so it's approximately 47. It got cut off. It's like 47 point something. It's 1/3 times this value. Yeah, so it's that divided by 3. All right, so now that'll give us our Ix. So what do we do with all of this information? So plug it back into like our general equation. So now we have, so Ix prime was the one that we were looking for, equal. So we have one rectangle. So we have 614.562.289 millimeters to the 4th. Now minus 2 of this value. So 114.159.26 5.4 millimeters to the 4th plus 4 triangles 3333.2054.68. All right. Now if we simplify that, that will give us approximately 520 times 10 to the 6th millimeters to the 4th. This is our final answer. Does anyone want to see how to show up the chart if you wanted to do it that way? Huh? I think he's going to give it to you, the chart. So, yeah, I'll do the chart. So then we would need the figure, area, I naught x, dy, a dy squared in that case. All right. So which of these values would we make like positive or negative? So let's say, so that's the rectangle, that's triangle, and this is the sector. So the sector would be negative, and there's also 2 of them. So we'd have to do, so 2 times which values? So if you're not sure, yeah, so look back at our equation. So I naught x, so that one would need to be, so that would be 2 times whatever the sector. Now would that be positive or negative? So that would be minus 2 times. Now do we need to make any of these others negative for that? ADY. So that would be minus 2 times whatever value you get for IX. Now what about for the triangles? 4 times the positive value for that, 4 times positive value for that, and then we'd be set. Does anyone have any questions on this problem? Yes? The triangle? Okay. So dy represents the distance from the x-axis, so like the axis we're taking a moment of inertia about, to the centroid of that shape. So in this case, it's a triangle. For a triangle, the centroid is located right about one here, which is 1/3 of that height. Now that height is 200 sine of 45. So we take that, divide it by 3, and that gives us our dy. Cool. Any other questions? Yes.
Could we have used symmetry in this case?
Can we use what?
Symmetry?
Symmetry? You mean like if we know the ones on this top half and then that half? So you could if you knew that shape, but do you know like what that shape even is? Like, do you know the moment of inertia for that shape? Yeah. No, so yeah, in this case you can't, so sometimes there's multiple ways to do it.
If we knew how to, if it was a regular shape, then we could have done symmetry.
What was that?
If it was a regular shape, say, I don't know, circles, something like that, we could have used symmetry.
Yeah, then you could.
So you could have done, so like cover up the bottom half and then 2 half sections, but that wouldn't work.
Yeah.
Yeah.
So sometimes you can do it that way. Sometimes there's multiple ways to do it. But thank you guys for coming. So I will post my solutions onto my WordPress site. If you could fill out that survey before you leave, I would really appreciate it. And thank you for coming again.